So welcome to our webinar on Geomet. My name's Cathy Evans and I'm the host of today's webinar. My background is as a mineral processing engineer or metallurgist, but I've spent the majority of my career in industry, consulting and research, working on understanding how ore characteristics affects their process performance in the concentrator. And having completed a PhD in Geomet, I'm happy to describe myself also as a geometallurgist. Currently, I'm a senior researcher at the Bryan Mining and Geology Research Centre at UQ, and I work with some fantastic postgrad students on solving some of the problems and interesting geometallurgical challenges. So let's start and have a look at geometallurgy. Often when I say I work in geometallurgy, people say, "What is geometallurgy?" So I thought it would be useful to look at how the people who work in this field define geomet. The first quote here is from Steve Waters, who was the professor who led the first geomet research project, the Amira P843 project, here at the SMI. And Steve's view was that geometallurgy is a more holistic, cross-discipline approach to maximising economic returns and managing risk. And those are words that we'll see quite frequently when we look at the range of definitions of geomet that are out there. So if we have a look at some of the other definitions, we can see that AMC consultants talk about geomet being multidisciplinary, and they provide a comprehensive list of the disciplines that can be integrated in a geomet program. These disciplines span the entire mining value chain. The other recurring themes are optimization and increasing value. Those themes are picked up again in the definition that SGS consultants provide on their website. The integration of information from a range of disciplines, the maximizing of value, and the minimization of risk, both technical risk and operational risk. And we see those same themes in the quote from Dean David, who's an experienced practitioner of geometallurgy. Again, the emphasis on cross-disciplinary nature of geomet and the focus on optimising profitability. So the quote from Steve Waters was a good summary of the consensus view that geomet is defined as a more holistic, cross-discipline approach to maximising economic returns and managing risk. So how does that definition work in practice? What drives mining companies to invest in geometallurgical programs? What types of business decisions does geomet help companies make? The example here is a common one, estimating the value of a parcel of ore, for example, a stope or a mining block. The inputs for this estimation come from knowing how the ore performs in crushing and grinding, how it behaves in the separation process, in this case flotation. Crushing and grinding relates to throughput, and the behaviour in the concentration process relates to recovery and product quality. So in this example, the inputs are used to estimate the production rate of copper metal, which obviously then links through to the metal sales into the market. How does current geomet practice differ from what was done in the past? Previously, the sampling of the ore body was often based on regions defined by geology or perhaps grade shells. These regions were then sampled for a limited number of physical tests to be performed, and the results of these tests were then taken to represent the entire volume from which it was sampled. With the low number of samples used in this approach, there are not many opportunities to account for any variation in processing response within the regions. With current geometallurgy practices, we seek to populate the mine block model with information about process response at the same data density as we have assay data. Given the number of blocks in the resource model can run into thousands or millions in the case of large deposits like Olympic Dam, it's obvious that we cannot perform that number of physical tests to provide the data needed to estimate process response. People working in the field of geometallurgy have developed tools and techniques to overcome this problem, and we'll talk about some of those later in the webinar. But why is that level of data density useful? At that level, we have estimates not only of how much metal is in each block, but in addition, what throughput can be achieved and what recovery we can expect. When that information is pulled into the mine plan, we can start to estimate metal production at different points in time across the life of mine. And this allows the business to forecast the cash flow with a greater level of certainty. Like any specialist discipline, geometallurgy has some terminology and concepts that are specific to the discipline. And all variability is an important aspect of geomet. In this diagram from the Bingham Canyon mine at Kennecott Copper, you can see the different rock types identified in their open pit. This is a good illustration of the concept of spatial variability, how ore characteristics vary across the volume of the ore body. Spatial variability is an inherent property of the ore body, created as the ore body was formed. The other concept that's equally important is the concept of temporal variability. And this is the variation in ore characteristics over time. In a geomet context, this temporal variability is related to how we mine the ore body. The sequence in which different parts of the ore body are extracted from the ground may provide opportunities to smooth variability that's present spatially. For example, zones of high-grade and low-grade ores could be mined in the same time period to provide a constant head grade in the feed to the concentrator. Of course, the ability to sequence ore types depends on a number of factors, including the mining method. Is the mine open pit or underground? It's not possible to mine the lower parts of the ore body first if you happen to have an open pit operation. Let's move on now to have a look at geometallurgy in practice. What are the activities that go into making a geomet program? The key to all geomet programs is access to samples of the ore body for analysis. And the starting point to obtain these samples is drilling, either reverse circulation drilling or RC drilling, or diamond drilling. The choice of drilling method depends on a number of factors, including the depth of hole required to access the ore body and cost. Both methods provide samples that are suitable for assay, which is usually the first analysis applied to the sample. Typically, the sample is divided into specific intervals, say 1 or 2 meters along the drill hole, and each sample is assayed. And this provides us with a 3D matrix of assay data across the pattern of drill holes and down each hole. And this type of data is used to define the resource. With RC drilling, the rock is broken as the drill penetrates the ground. And this drilling produces particles with a maximum size of around 10 millimeters, which are swept up and out of the drill hole by compressed air. The drill rig needs to have a well-designed sample collection equipment and procedures to ensure that all of the sample, including the fine particles which come out of the hole as dust, is captured and subsampled. This fine material can contain clays, for example, and if the sampling is not done in an unbiased way, you can end up with non-representative samples. And it gives you a very biased view of both the assay and the mineralogy. The type of data that can be collected from drill chips is limited compared to the information you can collect from diamond drill core. And it's limited by the fact that it's particulate material. Whereas in diamond drill core, you can see the texture. The rock is intact or relatively intact, and you can look at texture, the relationships of minerals across centimetres or millimetres and get a view of what the texture is like alongside the mineralogy. Diamond drill core does cost more per metre to drill than RC drilling, and sometimes budget is the limiting factor. But it does provide the opportunity to collect more information than RC drilling, just because the rock is extracted from the ground intact. You can collect information on orientation of features such as veins, mineral texture, and geotechnical information from drill core, which is not available from the RC chips. The size of core that you collect will vary depending on the drill string that's chosen. Typically, core is BQ or NQ, so 36mm diameter or 47mm diameter. But often if you're working on metallurgical testing and particularly comminution testing, then having the larger diameter PQ core, which is 85mm diameter, is needed to provide enough mass for those tests. So the samples collected in the GeoMet program are subject to a range of analyses. As a minimum, the geological data is collected by visual core logging, and that's often done by a relatively junior geologist. That material is assayed and density measured. Beyond that, the core could be scanned by one or more of the commercial scanning systems, which can measure mineralogy, as in hyperspectral analysis, or elemental composition leading to mineralogy, as in micro-XRF. Alternatively, representative samples of the crushed core can be sent for mineralogical analysis by quantitative XRD or MLA analysis. Geotechnical data is also obtained from drill core, with characteristics such as fracture frequency and rock quality designation, or RQD. RQD is an approximate measure of the degree of jointing or fracture in a rock mass, measured as a percentage of the total drill core that's present in lengths of 10 centimetres or more. Unconfined compressive strength tests and point load tests are destructive mechanical tests of rock strength, which require specific sample geometries and do require the geologist to give up pieces of core. Metallurgical testing can take many forms depending on the process route used to treat the ore from the deposit. Comminution tests are common, as most ores need to be size reduced by crushing or grinding before they can be separated. The types of tests deployed depend on whether the ore will be crushed and ball milled or sag milled then ball milled. As we'll see later in this presentation, the mass of sample required for these tests can be considerable and is often one of the limiting factors in applying these tests to samples at the same data density as assays. Separation tests used in a GeoMet program reflect the chosen separation route used in the process flowsheet, and depending on the complexity of the flowsheet, may require more than one type of separation test. As with the comminution tests, the separation tests can require many kilograms of ore, which when you're dealing with drill core is a limiting factor. And tests that are becoming more common as communities place greater focus on tailing storage facilities are the environmental tests, which measure the potential for ores to create environmental hazards when stored in waste storage facilities over extended periods of time. So you can see that the drill core that we remove from the ground has to go a long way. You have to have a careful plan as to what tests you're going to do and how you're going to divide up that material, as it's a limited resource. So having looked at the types of data we collect in a GeoMet program, let's have a look at how those different data types relate to one another. The P843 GEM project proposed this pyramid structure called the Geometallurgical matrix, which has multiple levels of information. The base of the GeoMet matrix at level 1 is formed from the assay data, and that's available typically for the largest number of samples. At the top of the pyramid at level 4 sits a much smaller number of highly characterised tests, usually metallurgical tests, which require large sample masses and are expensive to perform. A key aim of the geometallurgical matrix building is to ensure that intermediate levels of information exist that support the data propagation across the gap between the assay data on level 1, which is available for every sample, and the industry standard metallurgical tests at level 4, which are much fewer in number. These intermediate levels ensure that all processing performance test samples are fully integrated with a wide range of other attributes, such as mineralogy, scale-dependent texture, or rock properties. And it involves careful management of shared samples. One of the challenges in geomet programs is sample management, since the drill core is a finite amount of material, and allocation of samples to the various analyses needs to be carefully planned so you don't run out of material at a critical time. A common question I'm asked is, where does geometallurgy fit into the mining life cycle? Now, when do we start a geomet program? Is it just useful at the development stage? In fact, no. A geomet program can support a mining operation from exploration through to closure. This diagram from Nikki McKay, an experienced geometallurgist, shows how geomet is applied across the entire mine life cycle, with the blue triangle indicating the increasing ore body knowledge as the mine progresses from discovery to operation and through to closure. This diagram introduces the concepts of strategic and tactical geometallurgy. Strategic geometallurgy, which is represented by the blue triangle, has a long-term strategic focus and uses all of the relevant data from the Geomet database to predict process response in order to model the spatial variability of those responses through the entire life of the mine. The objective here is to enable better definition of the resource, to optimise mine planning and scheduling, to improve process design, and also to support the capital strategy of the business over the life of the mine. Tactical geomet, on the other hand, has a short to medium term focus, and that actively uses the Geomet database alongside data obtained from ore control processes during mining to decide whether mined material is to be delivered as ore, waste, or placed on a stockpile, based on the value of the mining block and not just its grade. So tactical geomet has a much shorter term focus and is using data that's been collected recently as part of the mining process. Of course, a key part of any geomet program is the characterisation of the ore. So let's have a look at the range of tools and techniques that are commonly used to perform the characterisation in geomet programs. As we've already said, the data that's available for almost every sample in the geomet sample set is the chemical assay of the rock. This is a bulk characterisation technique, and typically the assay data is available for 1 or 2 metre lengths of core along the entire drill hole and for every drill hole. As well as indicating the grade of the ore for use in developing the resource model, the assays can also be used to estimate the ore mineralogy. And it's for this reason that companies collect large suites of elements and not just the few elements of interest. So the large suite of elements allows the estimation of mineralogy from elemental assay. There are a number of methods that use regression techniques, which can be used to estimate mineral composition of the ore from the correct suite of elemental assays. These methods do require some prior knowledge of what minerals are present in the ore, and this information could come from the geological logging performed very early on in the Geomet program, or could come from the next tool that we'll have a look at, X-ray diffraction analysis. The graph on the right shows the relationship between the calculated elemental composition and the measured elemental composition. So we've used the elemental data to predict mineralogy, and then we have measured mineralogy, which gives us, we can calculate what the elemental composition should be. So generally you can get a good agreement between the calculated and measured, and it's always good to run a cross-check to make sure that you haven't missed some key minerals in the regression program that you're using. So X-ray diffraction, which is another bulk technique, it only requires a very small sample mass. The sample must be pulverized, but typically the sample would represent the same intercept as the assays, so 1 to 2 meters. So X-ray diffraction is based on analysing the crystal structure or the phases in the sample, and it produces a spectrum which can be analysed to provide qualitative or semi-quantitative mineralogy. Quantitative X-ray diffraction, or QXRD, requires a specialised analysis of the spectrum using Rietveld refinement. And this method is commonly performed in order to provide quantitative mineral composition of all samples that we need for modelling. There's specific software to do this QXRD, to perform the Rietveld refinement, and it often requires a skilled operator to actually run that software in order to get the best results. There are also techniques available to measure the characteristics of the relatively intact core. Hyperspectral imaging methods, including core scan and TerraCore, provide mineralogical and textural information across the core. The cost of these analyses can be around $30 per metre. The pixel resolution of these imaging spectrometers mean that their effectiveness for textural feature extraction is still a subject of research. Is the resolution at that scale useful to us? You can see from the images on the right that there is useful information at core scale. The challenge is that often the scale at which we require mineralogical data for process prediction is much finer than the resolution that these instruments provide at the moment. But there's potential for them to become higher resolution, and we can also use core scan alongside other techniques to give us data at the resolution that we need. So the outputs of core scan are these classified mineral maps that you see on the right hand side, and also a photographic image in RGB image, which lets you see the features and cross-check those in the classified image. So you can see that the classified image with gangue mineralogy and at the scale that it is potentially useful for modelling comminution. And we have research projects in progress at the moment looking at that exact challenge. Can we use core scan data to predict comminution characteristics of ores? On these systems, the mineralogical capability of each system is dependent on the spectrometer used. So visible and near infrared and shortwave infrared detects soft minerals, whereas the long wave infrared can detect the hard minerals such as feldspar and quartz. So in combination with the data typically collected, the RGB line scan images can give us some useful information about the visible rock features alongside those classified images. And then we have non-imaging hyperspectral methods, including the HiLogger developed by CSIRO and Geologger. And these provide mineralogical data across the ore body. But as you can see from their images that they produce, the data doesn't show the textural arrangement of the minerals across the core. Instead, each measurement point is represented as a band across the core, which shows the mineral composition at that point in terms of single or multiple minerals. As with the core scan systems, the mineralogical capability of each system is spectrometer dependent. And here, the near-infrared and short-wave infrared are used to detect soft minerals, and long-wave infrared is detecting minerals such as feldspar and quartz. A complementary tool which is beginning to be used in geomet programs is the micro-XRF system. Here, short sections of drill core, up to 19 centimetres long, can be analysed at higher resolution than the previous scanning methods. And here, X-ray fluorescence is used to identify the minerals based on their elemental composition. As well as quantifying mineral composition of the sample, these systems can also provide quantitative data about the mineral textures. And these provide a link between the mesoscale measurements in tools such as core scan and the microscale measurements that we can make of mineral texture using automated scanning electron microscope systems such as the MLA. So these systems provide what is currently a missing link between core scale measurements and the microscale measurements that we get from MLA or QuemScan systems. And I think we'll be seeing a lot more applications of these types of systems in geomet programs in future. The highest resolution analyses which we see performed in geomet programs are currently done using the automated SEM-based mineralogy systems, such as the MLA that's shown here. These high resolution measurements that these systems can perform are typically used to assess the mineral characteristics that link to process response. For example, grain size of target minerals, which affect liberation, or the association of minerals which contain penalty elements with the target mineral, which could affect product quality. While these systems can measure slabs of polished drill core, they are more usually used in geomet programs to analyse coarse particulate samples, say in the range 400 to 850 microns. The outputs from these systems include the images of texture that you can see on the right-hand side and quantitative data on characteristics such as grain size and liberation, which can be used in process modelling. And of course, alongside the mineralogical and textural characterisation of the ores, we also need to perform metallurgical tests to assess process response. Because of the limited masses of sample available from drill core, the tests in geomet programs must use smaller masses of sample than the standard tests. And because in geomet programs you want to collect as many test results as possible, these tests also need to be relatively low in cost and take less time to complete. The small-scale tests typically cover all aspects of processing which apply to the ore: comminution, flotation, or leaching as required. So let's have a look at two of the common comminution tests used in geomet programs. The comminution response of the ore affects the throughput of the plant and is key information in any geomet program. We'll compare the sample mass requirements of the small-scale physical tests and the industry standard bankable tests. So as you can see in the tables, the top table looks at the bond ball mill work index. So that's a standard test that's been around for a long time. And the standard laboratory test requires around 8 kilos of minus 10 millimetre particles. That can vary slightly depending on the lab that you're using, but that's about the size of the mass that's required. Alternatively, you can do geomet versions of those tests, and one of those is the JK bond ball mill test, which JKTech performs, which will also give you the bond ball mill work index. And here the sample requirement is half that of the standard bankable test. So 4 kilos of minus 10 millimetre particles. If we look at the drop weight test, which is an industry standard test for determining A times B, so the comminution parameter relating to sag milling. So a standard drop weight test requires 120 kilos of minus 63 plus 13.2 millimetre particles. So a very large sample mass. In some work we did at Ernest Henry in the past, we had to drill a twin hole along, so two holes, drill holes very close to one another, PQ size core, in order to generate enough mass to do these types of tests. So you can see the driver towards a smaller scale test would be a considerable cost saving, not just in the cost of the test, but also the cost of drilling enough material to perform the test. So the SMC test, which was developed to give A times B with a smaller sample mass in a geomet test, requires only 30 to 40 kilos of drill core. So as you can see, the ideal small scale test is cheaper, faster, and requires less sample than a standard test. And it's a challenge that researchers have been working on for quite some time. Certainly in the comminution space, there's been a response, and we now have tests which require much smaller sample masses. That challenge is still open in the flotation space. There is still no, I guess, widely recognised very small scale flotation test that we can use. So of course the aim of collecting all this data in the GeoMet database is to develop predictive models which inform integrated mine planning and processing strategies. And we do this by developing GeoMet models, which most typically would provide predictions of throughput and recovery. Ideally, these models are based on additive variables such as mineral grade or grain size, which can be readily propagated into the mine block model and allow the process response to be calculated for each block in the model. The throughput and recovery values for each block allow us to calculate metal production, which again allows estimation of the net present value of each mining block. And because ore body knowledge typically increases as we move through the mine life, GeoMet models are typically refined and improved iteratively as more data become available. And typically the drilling, there are several cycles of drilling in the life of a mine. So there are many opportunities to revise and improve the GeoMet model over time. An important point to note is that predefined domain concepts such as logged geology and alteration are not usually considered to be adequate for GeoMet domaining unless they've been validated or calibrated. So let's have a look at a very recently published example of GeoMet modelling from Olympic Dam's GeoMet program. And this is hot off the press from the Mill Operators Conference last week, a really good paper. And it's great that the team from Olympic Dam is willing to share their knowledge in this space, because it's difficult to find information about what industry is doing that's been published and about which we can speak publicly. So I'm always grateful to the Olympic Dam team led by Cathy Evans, who have a very large GeoMet program and are happy to share their knowledge that they've developed over a number of years now. So as I said, Olympic Dam's GeoMet program is an extensive program, and it reflects the size of the resource in what is a supergiant deposit. So Olympic Dam is an iron oxide copper gold deposit, and it also has uranium in the ore, so it produces multiple products from their site. And in their paper, they show that from their extensive database of 1,700 bond work index tests and their many thousands of assay samples, the Olympic Dam geometallurgists have identified a relatively simple relationship between bond work index, silicon assay, and ore density. Now, Olympic Dam has done extensive work, which includes mineralogy of coarse particulates, so they have a good view of the texture of their ores. But it turns out that for their ore type, they can use these relatively simple relationships. They don't need to go into very complex relationships. So they're very lucky from that point of view, because assay is there in every sample in their database. So with this simple relationship between the bond work index, silicon assay and ore density, they can calculate the bond work index for every intercept that's been assayed, and they can propagate that back into their block model. So now they have the ability to put bond work index into every block in the deposit. So bond work index across the entire deposit, not just in the 1700 regions where bond work index was measured. So the plan of the ore body that's shown on the right-hand side is across one of the mine levels, shows that when we have individual process predictions in the block model with their spatial relevance, we can start to see how useful that information is. The green zones show bond work indices in the range 14 to 16 kilowatt hours per tonne. But the work index climbs rapidly to 20 to 22 kilowatt hours per tonne in the red zones, some of which are very close to the green zones. So in a relatively small area, you can get quite a range of bond work indices. So if milling capacity had been a bottleneck in the process plant, this detailed geomet model of bond work index would allow the company to plan the mining sequence with that variation in mill throughput in mind, and to maximise the value and minimise the risk. Companies invest considerable sums of money in geomet programs, so they must believe that they get value from this activity. But as I said before, there's very little information published where companies have quantified the impact on their business of having a geomet program. But there is a comment from Dean David of Wood Consultants, based on his extensive experience in this area, which sheds a little bit of light on the value of geomet. So Dean says that stabilising an erratic SAG mill feed rate typically results in an average throughput benefit of 5%. And a 5% throughput benefit achieved through operational stabilisation typically translates to a 5% revenue improvement with little or no real capital or operating cost penalty. And that additional revenue at little or no cost equals profit. So we can get a view that companies which are deploying geomet and I guess providing budgets to cover the costs of drilling, analysing and having highly skilled staff to analyse the data and develop geomet models, those companies are, I guess, happy that it's a profitable activity for their business. And companies like BHP at Olympic Dam and also Newcrest have geomet teams. They have people whose title is geometallurgist. So it's becoming more commonly part of the way that mining companies do business. And it's the reason that geometallurgy continues to grow and evolve. I'd like to move towards the end of the webinar by talking briefly about some of the geomet research that we do at SMI. Geometallurgy covers the entire mining value chain, and there are lots of opportunities to discover useful applications of the tools and knowledge that we have. The first example here was a PhD project where the principles of geometallurgy were applied to a tailings dam. The tailings at this operation contained a significant amount of magnetite and in effect formed a potential future resource for the company as an iron ore deposit. By treating the tailings like a new deposit, Complete with drilling and geomet testing, the company was able to estimate the value of that resource on their site. The second project shown here integrated a range of tools to measure ore texture at different scales and identified relationships between mineralogy, texture and rock strength that are not only useful in a comminution context, but may also provide the opportunity to include geotechnical characteristics in geomet modelling. Another PhD project modelled the influence of vein and disseminated mineralisation in a porphyry copper deposit for use in a geomet model, and used the information on those different behaviours to domain the deposit. And the fourth example, at the bottom of the screen, is the testing of a potential small-scale flotation test, whose speed and low cost means it could be useful in geomet applications. Hopefully this shows you that the range of research topics reflects how much of the mining value chain is encompassed by geometallurgy. And we've got a range of fantastic students from across the world who are working on current projects now. So we've covered a number of aspects of geomet in this webinar today, but I'd like to summarise the key points as follows. Hopefully I've shown you that geometallurgy is a cross-discipline approach which brings together the expertise of geologists, mining engineers and metallurgists. Companies are applying geomet methods now and will continue to do that in the future to better understand their ore deposits, and their objectives in doing that are to minimise risk in the development and extraction of the deposit and to maximise the value. Quantifying the ore characteristics in geomet test programs requires relatively low-cost, rapid techniques to allow large numbers of well-defined samples to be analysed, and it's an ongoing challenge to develop tests which allow us to do that. And to date, there's no one-size-fits-all generic approach to geomet modelling. The tools and techniques applied are tailored on a deposit-by-deposit basis. I'll put some references there to the papers that I've referenced. Before we move on to our question and answer session, I'd like to talk briefly about some of our professional development courses here at SMI. And while I do that, please go ahead and type any questions that you have into the Q&A panel for our Q&A session. I think the course of most interest to people attending this webinar would be the Introduction to Geometallurgy course, which is a fully online course which starts on the 2nd of July, so very soon. This course is equivalent to a one-day workshop and is available online for 2 weeks. So you can study at your own pace and at a time that suits you. We've designed the course to suit people who are doing fly-in, fly-out, or people who are obviously busy during their work days and may only be able to study in the evening. So it's a very flexible delivery option, work at your speed at a time that works for you. There's still some spaces available on that course. So if you're interested, please go to the link on the SMI website to register for that course. And SMI has specialists working in a range of areas in mining, and we deliver courses on a range of topics, including process mineralogy, data analytics, deep mining geology, and risk management. So again, if you're interested in any of those courses, please go to the SMI website for more details. And our colleagues at JKTech have a range of upcoming courses too. They have open courses, which are open to everyone, and see JKTech website for further details on those courses. So courses on the JK SimMet software, JK Value Chain and JK MetSkill, and the Comparative Statistics course, which is a very well recognised course developed by Professor Tim Napier-Munn of the JK. And JKTech also offers in-house courses. So if you have a specific need at your site or within your company, you can contact JKTech for more information about what they can deliver to you. And of course, the next JK webinar in this series, Quality Control for Metallurgical Tests, is on the 28th of July. And as always, if you want more information on any of those, please head to the JKTech website. Thanks everybody for your attendance. It's been great to see so many people interested in Geomet. If you have any questions, then feel free to email me. My email is, you can find me on the UQ website. There's a contacts area on UQ, and I'm happy to answer questions. If you'd like to join us on the Introduction to Geometallurgy course, we'd be happy to have you. So again, just check the SMI website. It's an interesting area to work in, and one, as I say, it's a growing area and one that's continuing to develop. So it's been great to talk to you all. Thanks for your time. Bye.